This section of our course is about non-deductive reasoning, which we've called induction throughout our course. Those are just two different names for the same thing. We'll see that there are many different kinds of inductive reasoning and that the standards for judging them are different than the standards for judging deductive arguments. Let's begin by reminding ourselves of the difference between deductive and inductive arguments. At the beginning of the course, we said that a deductive argument is an argument that aims to prove its conclusion with perfect certainty. And an inductive argument, on the other hand, is one that aims to prove its conclusion with some degree of probability. Now, the probability of a conclusion of an inductive argument can be higher or lower depending on various different kinds of factors. And part of what we need to get at in this section of the course is what those criteria are for judging inductive arguments. Now, we know that a deductive argument achieves its aim when it's sound, that is, when it's valid and it has premises that are known to be true. Induction, on the other hand, it's quite a bit more difficult to say exactly under what conditions an inductive argument succeeds. This is a result in part of the fact that while we have a complete, robust, and unified account of the conditions under which all deductive arguments can be said to be good or bad, when it comes to inductive arguments, we have only a series of partial accounts. This is to say that inductive reasoning is harder to analyze than deductive reasoning. Our account of deduction has essentially been the same since Aristotle. We've elaborated a little bit, we've created new tools, we've invented some symbols and so on, but the basic idea of what makes an argument valid is the same now for us as it was for Aristotle. For induction, we've only had a series of partial accounts. Aristotle began the study of inductive logic in a serious way, and it's been continuing ever since Aristotle, so a couple of thousand years, and still we don't have a complete account. It could be that a complete account doesn't exist, or maybe we just haven't discovered it yet. What we do have, as I've said, is a series of partial accounts, which is to say that we have accounts of different individual kinds of inductive reasoning. So it could be that the reason that we don't have a total overall account is that we're trying to lump too many things under the same heading of inductive reasoning. Maybe what we should do instead is to treat them separately. Anyway, that's the approach that we'll be taking in the rest of this particular course. So here's a list of 5 of the most important kinds of inductive arguments. This is only a partial list. There are lots of other kinds of inductive arguments that we could talk about. For example, scientific reasoning and other things like that, explanatory reasoning, many other kinds of examples. But these are the 5 core, most important kinds of inductive reasoning. And if you can learn about how to critique these kinds of arguments, how to understand how they work, then you'll be in good shape. Now, this is important in part because we use inductive reasoning all the time in ordinary life, and in part because it's important in science and in the rest of education. So knowing about these will be helpful to you in the rest of your career in college and in your work life and in your life in general. We'll only be scratching the surface. We could actually have turned these 5 topics into an entire undergraduate course. So don't expect to have the whole story by the time we're done with these short videos. I'll try to do one video for each of these and keep it fairly short. That I hope will be enough for the purposes of this course, but there's lots more that you can find out about each of these if you do searches on each of these names online or in various other kinds of places like the library. So let's begin with enumerative induction. You could think of this as the base model of inductive reasoning. It's the standard for reasoning about evidence and reasoning about probable conclusions. And most of what we say about enumerative induction can be transferred to talk about the other kinds of induction that we had just listed. So how does enumerative induction work? Well, basically what happens is that you take a series of observation instances, those are reports about observations that you've made, and then you make an inference from those observations to some other claim. Now normally in an enumerative induction, the conclusion that you're drawing is called a universal generalization. A universal generalization is essentially the same as an A sentence from syllogistic logic. So the example in yellow that I've got in the middle of the page is that perhaps you're in Europe in the 1600s and you're walking around from pond to pond and you keep seeing swans everywhere, and you notice that each of the swans that you observe is white. So you observe swan number 1 and it's white, you observe swan number 2 and it's white, swan number 3 and it's white, and eventually you've observed some very large number of swans, and you'd be likely to draw the conclusion that all swans are white. So that's an inductive enumeration, or sorry, an enumerative induction, because you are enumerating a bunch of observations, listing them out, and then you are generalizing the result from those observations to all cases whatsoever. All right, so notice that there's a difference between everything you've observed of a certain kind having a property and everything of that kind having a property. So these arguments are always only probable, that is, we can't be certain that the conclusions are true. Even if we have some very large number of observation instances, we can't be absolutely certain that the conclusion is true. Now, we're likely to be very confident if we have a large number of observations, but that's different than being absolutely certain. The swans example is an interesting one because everyone was sure in Europe until the discovery of Australia by Europeans that all swans were white. But as soon as they landed in Australia, they saw black swans. And there's an important lesson there, which is that no matter how strong your base of inductive reasoning, then no matter how strong the base of observations from which you make your universal generalization, the universal generalization could turn out to be false. That's all we mean when we say that the conclusion is not certain. Now, in general, though, we should say that inductive arguments are very reliable. We use them all the time extremely successfully in ordinary life and in science. In ordinary life, you make this kind of inference when you do something like this, where you have a certain kind of new food that you've never had before, and you like it. You try it again later, and you like it again. You try it again, and you like it again. And you draw the conclusion that you just like that type of food in general. Okay, so that's an example of an enumerative induction from ordinary life. We also do enumerative inductions in science. For example, we have observed probably millions or billions of electrons by this point, and what we've noticed about each of them is that they each have negative charge. We draw the conclusion that all electrons have negative charge. Now, you could quibble with that. Maybe we say that it's part of the definition of being an electron, that an electron has negative charge. But certainly originally, at the beginning, when people were first working out the theory of electrons, they reached the conclusion that an electron has a negative charge based on a series of observations. Here's another example of an enumerative induction that's written out in the full form that you would want to use if you're going to analyze an enumerative induction. So you can see that the first premise describes the first observation instance. It says, in case 1, putting a piece of dry wood into a hot fire was followed by the combustion of the wood. And so on, right? You have some large number of observations, call that number n, and in all n of those cases, putting dry wood into the hot fire was followed by the combustion of the wood. It's natural to draw the conclusion from this large number of cases that therefore in all cases, not just the ones we've observed, but all the future ones, all the past ones that we didn't observe, that in all of those cases, putting dry wood into a hot fire is followed by the combustion of the wood. Okay, so one of the things you can say about enumerative induction is that the larger the number n of cases observed, the more probable the conclusion is, but you can never reach certainty. Another thing you might say about these kinds of enumerative inductions is that at the beginning, as you add more inductive cases, enumerative cases, then you are increasing the probability of the conclusion quite a bit each time. But once you've got already a very large number of cases, adding another one probably doesn't change the probability very much. So think about, maybe you've observed 10,000 swans and you've noticed that each of them is white. If you observe a 10,001th, is that what I'm trying to say? If you observe the 10,001 swan, you will, and see that it's white, that's not going to change the probability of your conclusion very much. Okay, so there's an interesting and complicated relationship between the number of instances and the degree of probability of the conclusion. Generally, though, the more instances, the stronger the conclusion, which is to say, the more likely it is to be true. Now, in a different kind of course, we might get into some of the philosophical puzzles relating to induction. In particular, the problem of induction is a very interesting one. It was put forward in its most widely known form by David Hume, a philosopher who died in 1777. The problem of induction is basically that it doesn't seem to be possible to justify inductive reasoning. We use inductive reasoning all the time, but there doesn't seem to be a way to show that such reasoning is justified. So that's a philosophical puzzle. It doesn't really affect the using of inductive reasoning, but it is an interesting philosophical puzzle. The second point that I call the mystery of induction is that even though we have the problem of induction and we don't have an account that allows us to fully justify the use of induction, nevertheless, induction is incredibly reliable. We use it all the time. So that's something that's an interesting philosophical puzzle worth spending some time thinking about if it's the sort of thing you're interested in. And if you take later courses in philosophy, you'll encounter those kinds of things. The last 4 examples listed here on this page are the kinds of things that you might study in a philosophy of science class. They have to do with trying to confirm a scientific theory with pieces of evidence. Turns out that there are logical puzzles that arise in that kind of endeavor. Also, if you're trying to falsify scientific theory, it turns out that there isn't a single way to do that. There's multiple different ways, and there's nothing in the evidence that decides the right way to do that. That's a really interesting philosophical problem, and so on. We unfortunately won't be able to get into these problems in much detail in our course, but it's the kind of thing that you could look up over the summer if you're interested, or you can take a philosophy of science class. Now, what's coming up next are a series of short videos about different branches of inductive logic. We'll start with analogical reasoning, and we'll go on to causal reasoning, numerical probability, and statistics. As I said, we'll only be scratching the surface, but I hope that it's enough to help you to begin a serious study of these kinds of inductive logic. And if you do that, I think you'll find it useful in all kinds of areas of your life. Let me know if you have any questions.